Good morning. My name is Robert Goldstein, and I'm here to talk about modeling of induction hardening and electromagnetics. I'm Director of Engineering at Fluxtrol, Inc., and I'm also a Fellow of ASMI International. So today we'll start by talking a little bit about what induction heating is, because it is different than other heating technologies commonly employed for heat treatment of steel components and other materials. We'll talk a little bit about how, because it's different, the modeling process for induction hardening, it has a lot of the same characteristics as other heating technologies, but also there's some particular features that we need to be aware of related to induction hardening as compared to other heating technologies. So the material properties for induction hardening, again, because of its specific characteristics, things are a little bit different. And finally, we'll show an example, a case story about axial scan hardening. And we'll walk from kind of how the technology started, how the modeling process began, and then how we built upon that to get to where we are today. And finally, we'll offer some thoughts on the future. So what is induction heating? Induction heating is a contactless heating method of bodies, which absorb energy from an alternating magnetic field generated by an induction coil. There's two distinct mechanisms of energy absorption involved in induction heating. There's eddy currents, which occur within conductive bodies and heating the part by ohmic losses. There's also hysteretic heating. Now, this only occurs when materials are magnetic, right? And if you look at steel heat treatment, the part typically will start magnetic, but it will finish non-magnetic. So the hysteresis heating is contributing only to part of the process. So in the principle of induction heating, we have a chain of phenomena involved, and this is just a simple cartoon to demonstrate the principles. So a power supply, its role is to convert line frequency 50 or 60 hertz power to controlled high frequency, high energy currents. So these currents flow through the induction coil, okay, and those currents themselves, they generate magnetic fields. Those magnetic fields flow in closed loops around the induction coil. When the magnetic fields come into contact with a workpiece, they induce a voltage in that workpiece. Okay, that voltage is what drives the eddy currents, which is the source of the eddy current heating, or those magnetic fields are what cause the change in the direction of the domains for hysteretic heating. So, and those eddy currents and hysteresis heating are what combine to generate your total energy in the part. So let's look at here an actual short video showing induction heat treatment of an automotive component. This is a very quick and efficient process. So the parts are loaded in the machine, indexed into the coil, heated, and quenched. Now that video is actually in real time. So more time is spent moving the part than actually heating the part and then cooling the part. Now, not all induction heating processes are so fast, but some are even faster. And that part was taken from room temperature to around 1800 degrees at a fine surface length and depth. The rest of the part is relatively unaffected. So let's look at what are the mutually coupled phenomena in an induction heating process. So this is what occurs just within the induction cell. We aren't talking about what's occurring before it, and we aren't talking about what occurs after. Right now, what we're looking at is what just occurs within the induction heat treating cell. And there's a lot of stuff going on there, from how the process is controlled, through how the part is heated or influenced by magnetic fields, to find how the part moves, the stresses that occur, and the structural transformations that occur. In addition, as you saw before, oftentimes there is quenching or cooling involved too. And all of those work together to get your component properties that exit the heat treatment cell. So what do we need to know about induction heat modeling for induction hardening? There's one principle that will not be covered in any of the other talks, and that's its principle of the electromagnetic reference step. Essentially what this is, it's an electromagnetic size. Okay, these reference steps determine how the current will be distributed away from the outer surface, right? In addition to some other factors. But you can see in the graph that in the first reference step, generally you have about 63% of the current, which results in about 86% of the power. Now, that reference step changes during a typical induction hardening process. So the formula is it's equal to a constant times the root square of resistivity divided by the frequency and the magnetic permeability. So that's how we're able to control the heating depth, by manipulating the frequency. But when the part starts, it generally has a relatively low electrical resistivity and high magnetic permeability. So generally the heat is concentrated very near the surface. As the part heats up, the resistivity rises and the permeability drops, especially once you're in the austenitic range, the permeability is 1. So there can be a drastic change in this electromagnetic reference step size, more than an order of magnitude, as you go through the process locally on the steel. The areas at the core in a surface hardening, they stay magnetic. So you end up with more complicated distributions of current in depth, such as what you see in the bottom right figure. So, and when we model induction hardening, the number of nodes that we need and the values per node that we need depend on whether that part is magnetic or not. And so we need very fine mesh when the part is magnetic. And that means that the solve times tend to be longer, okay, than the thermal portion. It also means that convergence on the results can be a little bit trickier, especially around the Curie point. So a lot of times we need very fine time steps there because the properties are changing quite rapidly. And to get it to converge on the proper temperature result, a lot of times you need a very fine time step and a lot of interim calculations in the solutions. This means that the induction process tends to be longer to model and require more elements and more real values and imaginary values than other heating technologies. So based on that, my mentor, Professor Valentin Nemkov, proposed the rule of pyramid, which basically says use more simple software to make your initial calculations, and you slowly then take that knowledge and build each step so that you have to do less calculations with the more complicated and time-consuming software. I can say right now, in today's world, there is no universal program that can solve all the problems of induction heating in a reasonable amount of time. For a 3D multi-physics simulation, generally the solve times can be in days to months for one case with very modern workstations. So you really want to limit the time you use at the top of the period. And what we found is oftentimes you can get 90% of the effort done just using 2D in a very reasonable amount of time, because the 2D solves now are very practical. So what are some of the factors that influence the accuracy of simulation other than am I doing 1D, 2D, or a 3D problem? So we look at it all depend on the process you're considering, okay, how much is going on, how much those multi-physics factors contribute to the results, the system geometry, the material properties, simulation type, okay. It's very common in induction heating. Typically, we simulate in the frequency domain rather than the time domain. The frequency domain, it ignores some nonlinearities that occur in induction. It assumes a sinusoidal current and voltage. When we deal with magnetic materials, especially early on in a hardening process where you typically have very high power densities, there is a lot of nonlinearity in the wave, and the exact level of error that causes is not really quantified and depends on the problem. The simulation method, whether we're using finite element, finite difference, integral, or some type of combination of the above. And finally, the algorithm. So all of these factors contribute to what will be the accuracy of the simulation. So, and then I'll talk a little bit about material properties. So which ones do we need to actually do the electromagnetic and thermal? So we need the density as a function of temperature, specific heat that's a function of temperature, the electrical resistivity is a function of temperature, and the magnetic permeability, which is a function of the magnetic field strength and the temperature. And this is, let's say, the classical description. But as we move more and more into induction heat treating, we're also finding that you go as these very rapid rates of heating like we've seen. All the phase transformations are also time dependent. So now we need to start thinking about those phase transformations are primarily what's driving a lot of these differences in the specific heat capacity. It also affects the resistivity and also affects the magnetic permeability. So these differences really should also be time dependent too, and incoming structure. So these are things we're still working. As we say, what is that accuracy? As we move farther along in the process of developing the models, things will continue to get better and better. That's why some of that ICME talks that you'll see are so important for us, and also to consider these non-equilibrium thermal transformations, which are typically involved in induction heat treating. And then the magnetic permeability of the steels, this is just some old notes that show, there's a lot of, let's say, unknowns related to it, and very difficult to measure those properties. So that's something that needs to be improved going forward. So with the materials databases for induction heating, we talked about how some of these things are dependent on the structure. And we need to understand how the steel will respond to these rapid non-equilibrium thermal processes. So, because all the databases, or most of the databases, have equilibrium properties. And if you just test things over long times, we don't maybe necessarily catch all of the interim transformations or interim structures that may form going from point A to point B in these very rapid cycles. And we're working to understand those better. So we've tried to collaborate a lot with the students at Colorado School of Mines and their Advanced Steel Processing and Research Center. There's also a number of other groups globally that are working on these problems that are hopefully continuing to help build that database for induction heat treating. So here's another example of the effect of short-time heat treatment on transformation temperatures. And some of the new things that have been evolving over the past several years, where there's been some observations. If you look at the blue circle, so this is typically kind of the range of temperatures and times that you see in a typical induction heat treatment. And what you notice is that generally there's an inhomogeneous austenite structure that's transformed to your finished martensitic properties. You can also see in this curve that both AC1 and AC3 tend to rise as time gets shorter. You can also see the temperature for the homogeneous austenite rises greatly. So whereas the furnace, you're almost always trying to get into that homogeneous austenite zone. Well, with induction, we are typically working in the inhomogeneous zone. Another thing we can look at here is the the flash bainite structure, which has been shown to have good elongation, reasonable hardness, and low carbon steels. They're going way above the AC3 in this inhomogeneous austenite range over very short times and finding good properties. We also see another area of exploration by Bob Kreiderman recently, where he's been going below the AC3 and above the AC1 and finding excellent bending fatigue results for 0.55 and 0.6 carbon steels, which are usually not selected for those type of properties. But he's been getting excellent properties in a region you're typically told to avoid. So it's all these things we're working to understand as we work at this non-equilibrium thermal processing. So then we also need to look at, okay, so how do we optimize that process and cycle? How we relate those material properties to actually the part performance, right? And how that relates to things like the alloying additions. So here's an example of a study done by Dr. Rothleutner, while he was at Colorado School of Mines. And what he found is that the addition of vanadium, a microalloying element, is not significantly different from 1045 for medium and high conditions. But for low loading conditions, he found a significant improvement in the performance. It added 2 points of HRC for case hardness and much finer prior austenized grain sizes, which believed to contribute to the strength of that. So to predict a component's real performance, we need to consider all the layers that comprise a component. Okay, everything is not heated to equilibrium. In fact, induction, while it's a volumetric heating, there is a bias, as we showed with that reference step slide, to power near the surface and depth. But the component is made up with more than just the surface, and all these layers that each undergo a different thermal cycle result in different properties of different layer, and the performance or strength of the component is due to the sum of all those layers. So if you look here, another slide is the impact of the incoming processes on the resulting component properties. So this is some results done on the Glebel by Dr. Whiteley while he was at Colorado School of Mines. And what he found is, depending on different incoming structures and different incoming processes, the induction would have, and the alloying elements would have a different level of impact on reducing those prior austenite grain sizes, which are highly correlated to the strength of the overall component. And so you can see that all these factors are interrelated, and what's going on beforehand really affects the final property. So finally, I've come up with this new slide now, which, a lot of people in science like to relate things that they're doing to things that naturally occur or occur in nature. So when I look at the structure of a induction heat treated component and thinking about that layered approach, it's almost could be related to, a tree and the rings of a tree. So each ring of a tree is formed and has certain properties based on the conditions that it went through in its life. Now, and the strength of the overall tree is really the sum of all of those rings. So, and even it kind of looks a little bit like a case hardened example. So this slide was this picture was from NASA. So, and you can see things like damage that occurred during the life of the tree. Well, that can cause a defect later on. Whereas if we look here, if there was a defect in the steel before, that can cause a fracture that can be started or failure that occurred during the induction heat treating process. So Let's go to axial hardening now, a case story, something practical people can understand rather than some of these principles. Here's an induction hardening machine. Again, the parts load up. Now, this one won't be quite as fast as the other one. The other one was likely a 2-3 millimeter case depth. This is likely a 6 to 10 millimeter case depth. So you can see initially, parts index in position, starts to heat. Then you see a quick jump out so that you don't overheat the bearing. And then you see this continuous part of the process where the heating is occurring on the shaft and immediately the heat's being removed after due to the quenching. Typically, a 1 meter long axial shaft will take somewhere between 90 seconds and 3 minutes to scan, depending on the case depth and diameter. Typically done in 2 spindle scenario. Sometimes more spindles, sometimes single spindle, but most commonly 2 spindles. So let's look why all these axles are induction hardened or shafts. Especially for torsional components and torsional applications for heavy loads, it's been found that generally induction hardened components perform better. And that's even despite having less carbon content typically or less alloy content than typically used for other technologies. So here's another study. Again, this is from a great handbook, ASM Volume 4C. This article is written by Professor Janis Groom, who's done a lot of great metallurgical work on induction heat treating over the years. So here's another case where the induction hardened component significantly outperformed the other heat treating methods tested. So people have known that for torsional applications, induction heating components generally perform better. So let's look at some of the things and understand why that is through modeling helps us to understand that. So axles initially were developed empirically. So the first induction scan hardened axles started to appear in the period just after the Second World War, and they replaced furnace hardened components. Mainstream adoption of the axial scan hardening was in the 60s to 80s. And there they set out all of these different parameters as far as during this big empirical study where they started to understand what are the relationships between the key factors that will lead to the best torsional performance. So the empirical development, it went through a lot of changes. Initially, they started with motor generators, replaced by solid state inverters, which were much more controllable, much more flexible, and much more efficient and require less maintenance. Development of rules of thumb for the relationship between the frequency, scan speed, and case depth. Went from single spindles to multiple spindle machines, sometimes even up to 6 spindles. The introduction of polymer quenchants. So single turn coils were replaced by 2-turn teardrop coils for increased productivity. Modern controls and energy monitors to really understand and know if you're repeating the same process. And then slick little development for roller systems that would reduce the shaft distortion and dimensional movement during the process. So then when I started in the industry in 1998, it was just the very beginning of the transition from experience-based design to computer model-driven design and induction heat treatment. It was just starting to transition from an academic experiment to a practical tool. So it's been an uphill climb. And some of the barriers to transition we experienced were, it's a complex problem. And great effort was put into the development of the solutions, and they were pretty good. I mean, they were making good parts. Most people who knew how the process was developed were not the people that used the process. And many of the people who developed the process were no longer working in the field, so that knowledge base was disappearing. So, and most people using them only knew that it worked. And if they changed too much, there would be a problem. So computer models, and finally, computer models were new, and there was a lot of distrust because there was a lot of, let's say, questionable modeling done early on. So if we start to look at 1998, where we were, so we had that process chain we showed before. And at that time, we could really only do electromagnetic and thermal in 2D. 3D coupled problem was not practical at all. So really, we were talking about electromagnetic and thermal in 2 dimensions only. So over time, things got better. So this is an example from 2000 of ELTA. While it was 1D, we could actually move the part, which was key for understanding the full thermal cycle the steel went through. Also, in the 2D, we demonstrated like static models in the dwell, which were good for making the pattern at start, which is a lot of times the most difficult part of the process. But it was difficult to really predict, well, what impact would that be on the overall process? Also, the computer hardware. So, and I just put these slides up there. When I was in college, we didn't use zip drives, we used floppy drives. So I saw, or high school, I saw the development of portable storage from, hundreds of kilobytes up to a couple megabytes, up to 100 megabytes for a zip drive, up to almost 5 gigabytes for a DVD. Now can fit close to a terabit on a little USB stick that easily fits in your pocket. So another thing to keep in mind is that Windows was only 32-bit. And this only allowed for the use of 2 gigabytes of RAM maximum per problem. In reality, once you get some of the overall interface, you really kind of have about 1.4 gigabytes of RAM that you could use. And this strongly limited the ability to solve 3D EM problems. You just couldn't get enough elements to get an accurate solution without too many compromises. And the other thing, if we look at in 2001, is that workstation that we were using then, it would be blown away by the modern cell phone that comfortably fits in your pocket. So definitely the hardware has made a lot of development, which has helped these things over time. So here's some pictures from the old models, but we could start to use that to understand, okay, how frequency, how concentrators, other things, how they help us to manipulate the pattern during that dwell starting process, and how the heat's being distributed in this non-uniform geometry. It's an axial. In 2003 or 4, then we got a big step forward, which is now we could model the electromagnetic and thermal and the motion. So this really told us what is going on in the process. Now we understood why the 2-turn teardrop was able to work so much better than a 1-turn, why the recipe was developed as it was, and what were the limitations of the current technology out there. This led to proposals for an optimized inductor that was machined, profiled, and with the appropriate magnetic flux concentrators. It led to a more robust and repeatable tool. It improved the distribution of heat in both the dwell and the scan. It led to a better heat pattern in the dwell, improved scan speeds with significant energy savings, and then reduced dimensional movement potential due to reduced core temperatures for the same case depth. It also suggested the potential optimal solution with higher frequency for the dwell and lower frequency for the scan, which now is actually possible. At that time, it wasn't implementable. But new machines such as Inductoheat IFP, power supplies, and there's some others now that have more flexibility out there where we can actually implement this in the process and further improve the performance and productivity of axial hardening machines. And that might lead to different optimal designs. So we had this concept. Now we had to find a place to test it. So to take it from paper to practice. So we partnered with a tier one automotive parts supplier in Mexico. And they, of course, the only way we got this opportunity was because they were having great difficulty to produce a given component. Always problems are opportunities. And we need to embrace those opportunities and challenges to advance. So we actually built this coil based on the computer models, and we took it down to Mexico. And you can see this table. This is actually directly from the customer's internal report. And you can see the labels up front: test 1, test 2, test 3. Those were test 1, test 2, and test 3. Right after we took it out of the box, we put it on machine. This was test 1 that we used from our virtual cycle that we had made on the computer. And you can see that we're almost right in the middle of the spec throughout the shaft. And then you also see that at the 45, which was the area they were having difficulty getting 90 thousandths effective case depth in without through hardening the bearing right above it, we were at 150 thou. So not much less than actually the distribution in the shaft. And that was at 20% lower energy. So you see 20% potentia minus, that's energy. So we produced a better part, at least according to the print, with 20% less energy on our first trial. Later, we played with the speed and moved things up and kept everything in spec along the way. And we're going 20% higher speed at 2% lower power. So this was great. The people at the plant were excited. They're like, this was a large induction heat treating plant. They're like, we want you to convert all of our machines and all of our coils to this style. And they sent the results up to corporate to show them the advancements that they had made. Unfortunately, it got up to corporate, and corporate said, whoa, hold on. We need to PPAP this. Like, what do you mean it's right in the middle of spec? They're like, yes, but we've never been in the middle of spec. And this part is too different from what we know. So that's when we started to understand that there is more to this process than just modeling in the picture on the page that's the target. So to help improve the capabilities of what we call virtual prototyping at the time, because now we're prototyping a full process, we need to understand better this metallurgical stress and dimensional movement, because these things were critical in understanding actually how the part would perform in the field. So we partnered with Dante Solutions because they, one, were kind of adventurous folks like we were, and they also had specific metallurgical expertise, with us being electromagnetic and thermal people did not have. And once we took and coupled our electromagnetic and thermal results with their thermal, structural, and dimensional movement results, we really started to learn a lot more about what's happening dynamically inside of that shaft and provide us with the information that we're going to need to communicate with production engineers and plant and corporate and plant metallurgists. And we also added Greg Fett to the team, who was at that time the chief metallurgist from Dana, who was the world's largest producer of axles, and now is a retired consultant for heat treatment. And Greg had kind of written a lot of the defining articles about the relationships between steel structure, case depth, alloying content, and loading capabilities. So one of the things we started to look at is the effect of the spray quenching rate on residual stresses. And this taught us a lot, that it's been known that, if you quench too strong a quenching can potentially lead to cracking, or too low a quench can cause insufficient hardness. So as we look at this, we start to see that, wow, we're really increasing our compressive residual stresses as we increase the quenching rate. We also were increasing the tensile stresses, especially at the start of the process and at the case core interface. So there was this relationship, this push-pull, where both were being affected. And we need to be cognizant of both to maximize the part performance. Another thing is, with these additional stresses, we found out that actually the axial growth of the axle depended, and radial growth depended on that, that those stresses were higher because the axle was actually moving more, which was really interesting. If you see that bottom slide with the very intensive quenching, the axle actually grew 2.3 millimeters, whereas it only grew a couple tenths of a millimeter with the slow quenching. The other thing that we saw is the radial dimension. That also changed, but not nearly as much as the axial. So what we saw was that these things were really moving a lot during the process. It explains why some of those things, when they'll have a top center that constrained the axle, was causing a bowing or bananaing of the axle shaft, which is why those constraining rollers really helped to keep things aligned in the induction coil and the part straighter. So once we had those residual stresses, now we looked at, okay, well, how can this part carry a torsional load? So how do we simulate the testing process? There isn't the test capacity there used to be back in the day, like when they developed all these Axial recipes. Nowadays, test time is really, really at a premium at corporate headquarters for metallurgy, and typically these aren't available in plants. So to actually virtually test a part to see if you've improved the process or not, or improved the part performance or not, or if it's going to survive, takes a lot of time. It can be a deterrent to a new development implementation. So we looked, well, can we study this virtually again? So actually test how the component will bear the loads. And sure enough, Dante was able to incorporate that in their model and look at different torsional loads, a low load and a high load. And we could see that the impact that these residual stresses from the process were having on the ability of an axle shaft to carry a torsional load. Just as an example here, if we look at where we have a principal stress with, this is the exact same pattern. This is just if we just took the structure and modeled it without residual stresses from the induction hardening process versus modeled it with the residual stresses from the induction hardening process. And you can see that at the, if we looked at like a 900 megapascal, which is probably pretty close to the principal stress the component could take, you'd see that that occurs at 7,500 Newton meters of torque. Meanwhile, if you consider the residual stresses, we're only at 300 megapascals of stress, well below the low carrying capacity of the component. So you can see that if you look at the shift, it's almost like a 5,000 Newton meter of torque shift in the curve. So the induction hardening, if you were to be able to extend the curve, likely would be able to carry close to 12,500 Newton meters of torque as compared to the, and without those residual stresses only taking 900. Only taking 7,500, sorry. So the component failure, so this residual stress has also impact the crack angle. And this was another really interesting finding. If you look at low torque levels, so your fatigue cracks, they're going to tend to occur with the residual stresses modeled at a lower shear angle. As you increase the load, it approaches 45 degrees. If you do not consider the residual stresses, you only see a 45-degree angle. Before we can see it, always stays under that. When presented with these results, Greg Fett shared his work, which showed you can see visually in the pictures the difference in the crack angles between a fatigue crack and an overload crack, and neither one is at 45. But there's definitely a much lower angle for the fatigue cracks and the overload cracks. So these type of results now are really catching the eyes of metallurgists and understanding that the modeling process has come a long way, and now this can be a practical tool to virtually simulate the cycle. If we look back to where we were in 1998 and where we are now, we can simulate the whole process chain that's occurring in the induction heating cell. Okay. Now, keep in mind, like we showed you some earlier slides before, that's not all that's going on. So in the future, we're going to continue to model more and more and more of the manufacturing chain to build the component virtually from cradle to grave. So this is going to need more interdisciplinary teamwork. So we can't really expect one person to be an expert in every process along the supply chain, nor can we expect one software to completely model every step along every supply chain well. There is significant process in a lot of these multi-physics tools, but we're not there yet, but we are progressing. And over time, modelers will hand off to other modelers and will just walk right through the chain, and parts will be developed virtually. And we'll be able to make changes on the fly rather than having to wait for prototypes. And it will compress the development schedules. That's really what's driving this increased modeling and part development, and also the needs for better overall material properties. The other thing we can predict is that there'll be more needs for vehicle lightweighting, and this will drive completely new solutions. Over here, I've just kind of given an example of some multi-material components being developed at the Institute for Machines and Forming in Germany, and some collaborative work we did with some of their students and Dave Geisberg from QA Metallurgical. So you can see here, steel, aluminum, steel, different forming temperatures, different thermomechanical processes, which would be followed by then a heat treatment. And you can see that because of the specifics of the induction process and the times and local temperature gradients, we're able to form really good-looking metallurgical joints between two highly dissimilar materials. And this is creating the potential then for actually, driving these multi-material components where you tailor the properties and materials of a given section of a component to the needs of that section of the component to lead to the overall optimization of the given set of performances the part will undergo in the field. And not just within one part we're going to virtually model, we're virtually model whole assemblies and how they're all working together in order to maximize performance of a set of components that perform a goal. So conclusions, over the past 22 years, we've made a lot of progress in understanding the induction hardening problem. However, there's still more work to do. So as I stated, our goal when we first started was to fill that circle, right? That process chain within the cell. We thought that was the top of the mountain. Now we've kind of, it's 2020 and we've kind of got to that point, but we realized, no, we're actually not at the top of the mountain. It's still over there. And we don't really know exactly where it is, but we know we're going to keep going that way. and things are going to force us to go that way. So it's kind of an adventure. So finally, I'd like to close with acknowledgements and the people that have helped me along our journey and my journey. One's like Dr. Valentin Nemkov. He was my mentor and teacher in induction heating. Bob and Rick Ruffini for continuing to support the research and other collaborative research that we get to do at Fluxtrol. That don't necessarily drive the short-term bottom line. Other people that I've worked with at Fluxtrol CIT over the years, Lynn Ferguson and the rest of the Dante team, stress, deformation, part loading, and failure models, Bob Kreiderman, the rest of the CSM team, Jody Burke, currently at Charter Steel, formerly Delphi Ajax Taco Gerdau, Greg Fett, helping us with a lot of the papers and understanding more about the real performance and needs of the components. Rob and Darren, others at Inductor Heat, sharing with videos and some laboratory time at different steps along the way. Dave Geisbert, metallurgy on the bimetal shafts. Professor Barron's group at the University of Hanover for the bimetal shaft work. And many other companies have been brave enough to test new ideas. So thank you very much. I'm available for questions.